And we can look very far away and find huge numbers of objects. This picture shows a patch of sky so small it would take 100 patches like it to cover the full moon in the sky. This patch would look just blank, looked at through a small telescope. But with a very big telescope, you see these hundreds of smudges. Each of these smudges is a galaxy. Many of these galaxies fully equal to Andromeda or our own galaxy. The light from some of them set out 10 billion years ago, when we knew when they were only recently formed. Some consist mainly of glowing diffuse gas that hasn't yet condensed into stars. When we look at Andromeda, we might wonder whether there are aliens looking back at us, perhaps with bigger telescopes. Maybe there are. But the light we see from these ultra-remote galaxies is set out before there's been time for stars to forge the silicon, carbon and oxygen needed to make the planets. So there's a scant chance of life on any of these galaxies as we see them. Incidentally, just as a digression, people sometimes wonder, when they look at the universe now and they're told it started from some dense Big Bang, how did an amorphous, dense Big Bang end up in this complex structured state? It seems contrary to the famous second law of thermodynamics that tells us that generally structure gets washed out and homogenized. The reason why is the fact that gravity is a dominant force. And what happens as the universe expands is that regions that are slightly denser than average to start with lag behind more and more and eventually condense out. Density contrasts grow. So only tiny irregularities of the early universe, when it's small, are enough to develop into the structures we see today. And the next movie I'm going to show shows a region of the universe, simulated computer, big enough to contain about 1,000 galaxies. The expansion of the universe is subtracted out, so it looks the same size. That's when you see the structures develop. At bottom left, you see the time in billions of years. And you see the structures gradually develop. So get the lights down, you see it better. And so this kind of model shows how starting from a smooth universe, you can end up with something rather like what you see. If I needed a logo for my research group, I'd choose this, called Ouroboros. And this image depicts rather nicely the interconnectedness of the micro-world on the left and the cosmos on the right. Smaller scales on the left, they go around to the big scale on the right. And there are links between small and large, between left and right. Our everyday world, life and mountains, is determined by atoms and chemistry. Higher up, stars are powered by the nuclei within those atoms, so it's a link really halfway up. And higher up still in the picture, there's another link, to have no time to address in this talk. Galaxies are seemingly held together by swarms of particles that make up the so-called dark matter. So there are links between atoms here, between nuclei within those atoms and stars, and the links between subnuclear particles and galaxies. Left is the domain of the quantum. The right-hand side is where Einstein's theory of gravity holds sway. Now, general relativity and quantum theory are the two twin pillars of 20th century physics. But they haven't yet been meshed together in a single unified theory. And in most contexts, this doesn't really make any difference. It doesn't impede science, because their domains of relevance don't overlap. Astronomers can ignore quantum fuzziness when they're studying the orbits of planets. Conversely, chemists can safely ignore gravitational forces between the atoms in a molecule, because they're nearly 40 powers of 10 weaker than the electric forces. But at the very beginning, everything was squeezed so small that quantum fluctuations could, as it were, shake the entire universe. And to confront the overwhelming mystery of what band and why it band, We need a unified theory of cosmos and microworld. To put us on a firm footing, we need to understand the synthesis at the top of this world for us. Symbolized as a gastronomically here, the very smallest things there, the very largest there. And we don't yet have such a theory. But before leaving this picture, let me notice the third frontier at the bottom, the very complex. We ourselves are midway between atoms and stars. Are large enough compared to atoms, have layer upon layer of intricate structure. We're not so large that we're crushed by gravity. To understand ourselves, we must understand the atoms we're made of and the stars that make us. We are literally halfway, in a precise sense. The geometric mean of the mass of proton and the mass of the sun is 50 kilograms. In fact, with 2 of the mass of each person here. So it takes about as many human bodies to make up the sun as there are atoms in each of us. But stars are simple, just like atoms are simple. Stars are simple because they're so big and hot that their content is broken down into simple atoms. Stars don't match the intricate structure of even insects, let alone the human brain. And I'd like to show you this picture. This is from the Royal Society's first bestseller, Robert Hooke's book, Micrographia, where he did wonderful drawings of the insects that he, for the very first time, saw with a microscope. And he remarked on the intricate structure of the animal world compared to anything which could have been made by humans. I just want to put a health warning or hazard warning. Now, I want to make a few rather speculative remarks. First, one interesting question is, how big is our universe? Is it even bigger than we can observe? Now, we can see a huge volume out to the limit of our telescope. You can see it about 10 or 15 billion light years. But that's a finite volume, because essentially there's a horizon, a shell around us, delineating the distance light can have travelled since the Big Bang. But that shell around us, that horizon, has no more physical significance than the horizon around you if you climb the mast of a ship in the middle of an ocean. You don't think that the ocean necessarily ends just beyond that horizon. And likewise, we would expect far more galaxies beyond the horizon of observation. We don't know how many, but most people guess that the universe goes at least 100,000 times further than we can see. The reason for that is if we look as far as we can in that direction, conditions don't differ by more than 1 part in 100,000. So if there's some sort of gradient across some huge domain in space, it's a very gentle gradient. And indeed, the space could extend far, far further than that still. Indeed, space could go on forever, more like an infinite flat Earth with a finite ground. And if that's the case, our universe would be vast enough to harbour an infinite variety of duplicates of ourselves. All combinatory options would happen somewhere. This universe would be room enough to exhaust all possibilities. Another lecture like this with other people in it. All this far, far beyond the horizon of our telescope.